Swayam Prabha. Digital India. Educated India.
Good morning to all of you. So, today we have come almost to the final portion of the drift flux model. See, in the last classes what we had derived is, we had derived what is a drift flux model, and then the concept of drift flux, and then how the drift flux can be incorporated into different expressions of the mixture properties, like the mixture density, the in situ velocities, and so on and so forth. And finally, we had derived the final expression of the drift flux model, which gives us as J2, this is equal to J21 plus alpha j. This was what the final expression we had derived, from which we had calculated alpha, and and accordingly that alpha was substituted in the different expressions. Now, the first thing which I would like to tell you in this class is, when we had written down this particular expression, this assumes that J2, J21, they are constant over the entire cross sectional area, isn't it? This was the first thing that we had assumed, that well we take an averaged value of these particular parameters averaged over the entire cross sectional area. Now, usually we find that this can be a very drastic assumption for most of the flow situations. For most of the flow situations, we find that usually they keep on varying across the cross section. Okay. So, a corrected expression for the, in order to incorporate the average quantities averaged over the entire cross section, the best thing will be to average it out. Now, whenever we write down averaged over the cross section, we usually denote it by this particular symbol. What we mean is, actually whenever we are writing this expression, what we mean is that all these quantities are averaged over the entire cross section. Okay. Where this particular quantity, say J2, or for any particular property P, okay, for any property P, your this particular this squarish brackets, they basically mean integral P dA by integral over dA integrated over the entire cross sectional area, or in other words, this is 1 by A integrated over A integral P dA. Okay. So, therefore, you can very well understand that when I put these brackets across the individual terms of these expressions, what I mean is, this is the average volumetric flux of component 2 averaged over the entire cross section. This is nothing but basically integral J2 dA by A. Okay. This is the average drift flux which is averaged over the entire cross section, and this is the product of volumetric concentration and volumetric flux which is averaged over the entire cross section. Well, would just like to make a correction, they are all referred to the two phase values. Okay. Now, therefore, we find that all of them are the average quantities, where, as I have told you, this particular bracket for any property, this simply denotes the area averaged value averaged over the cross sectional area. And the void fraction, there are two terms. One is, since for single phase flow, this is a sufficient definition, the area averaged value of each property, or rather for any property, this is nothing but the area averaged value for property P averaged over the entire cross section, averaged over the cross sectional value. averaged over the cross sectional area. Okay. And when we are having two phases, then we know that both the phases do not occupy the entire cross sectional area. Say phase 1 occupies A1 part of the area, phase 2 occupies A2 part of the area. Under that condition, there is one additional definition which is void fraction averaged weighted mean value, or void fraction averaged mean value. The void fraction weighted mean value means it is weighted against the void fraction. This is for any particular property for phase I or k, whatever it is, void fraction weighted mean value of property P. This is P k bar, this is nothing but alpha P. Say if it is P2, then alpha P2 by alpha. Okay. If it is P1, then it is 1 minus alpha P2 by alpha. Okay. So, this is one particular term which is very, very important. So, if you observe this term, you find that here alpha JTP will be equal to nothing but alpha into JTP bar, is not it? It is something of this sort. So, what it is that we will be noticing, or alpha into P2, alpha JTP, this is going to be in that in the other particular fashion. So, therefore, we find that there are two particular definitions which we have to keep in mind. This you have already got in your single phase flows. For any property P, the area averaged value, when the area is averaged over the entire cross sectional area, this can be given by this particular form, and the weighted mean value of the property, that is weighted over the entire, or the void fraction weighted mean value, it is can be expressed in this particular form. Agreed. So, accordingly we find that if this is true, then accordingly the different mixture properties which we get, they should be averaged over the entire cross sectional area. So, therefore, just like I have written it down for J2, similarly for rho Tp also I can get the expression. So, suppose I get it for rho Tp, what was it? This was alpha rho 2 plus 1 minus alpha rho 1, is not it? Now, for this particular case, it is the mixture density averaged over the entire cross section. This will be alpha rho 2 plus 1 minus alpha into rho 1, where we assume that rho 1 and rho 2, they are constant over, they do not vary over the cross section. And this particular assumption, remember, this is a valid assumption because the transverse pressure gradient constant, because we find that the transverse pressure gradient within a channel is relatively small. So, therefore, this is a reasonably, this rho 1 rho 2 being constant is a reasonably valid assumption, and under that condition the mixture density, the correct expression is in this particular form. Remember, after we finish the drift flux model, we will not be putting curly brackets everywhere just because it is very cumbersome, but we will imply that when we just say alpha, it is the area averaged values. It is implied that after this particular topic is over, when we write alpha, we mean this, okay, unless otherwise stated, okay, because every time writing this down is difficult. So, when you are just expressing it alpha in this particular way, it is the mean averaged values. In the same way, we find, say, the axial component of weighted mean velocity. Suppose the U2, axial component of weighted mean velocity, okay, of phase 2. So, this is going to be U2 bar. If we write, this is alpha U2 divided by alpha. Agreed? Now, we know what is alpha U2 equal to. Alpha U2 equals to, this is the void fraction multiplied by the in situ velocity of component 2. So, therefore, this gives you J2. So, therefore, please remember that a axial component of the weighted mean velocity of phase 2 u2 bar is the average J2 divided by the average alpha. Please remember, this is not equal to this u2 bar, which is equal to this is not equal to average u2. This is the weighted mean, this is the cross sectional average. The void fraction weighted mean velocity, this is the cross sectional average velocity. These two are not equal. Why? This is equal to the cross sectional average of J2 divided by the cross sectional average of alpha, whereas this means J2 by alpha over which the cross section is taken. Are these concepts clear to you? Please try to understand these concepts, they are extremely important. The thing is, in this particular case we get, this is the weighted mean average velocity and this is the and this is the cross sectional average velocity. What does this mean? This u2 bar, it means, this means integral u2 dA 1 by a, or in other words what it means? It means if this is equal to J2 by alpha, this means 1 by a integral J2 by alpha dA. That means for each particular point you measure J2, you measure alpha, you divide the two, get the product, then get the quotient, and then that quotient you integrate over the entire cross sectional area divided by the area, that gives you the weighted mean average velocity. Okay. And when you talk of u2 bar, that is it gives a cross sectional average velocity, very sorry. And when you talk about the weighted mean average velocity, this means J2 by alpha, which is nothing but equal to 1 by a integral J2 dA by 1 by a integral alpha dA. Now, by comparing these two expressions, is it clear why this is not equal to this? This is the cross sectional average velocity of component 2, this is the weighted mean velocity of component 2. So, they are grossly different. For this, what you have to do? You have to measure the local or the in situ J2 at every point, the local or the in situ alpha at every point, divide the two, find the quotient, then that quotient to integrate. In this particular case, it is much more easier. What you do? You find the cross sectional average J2. Finding out cross sectional average J2 is very easy. This is nothing but Q2 by A. So, therefore, this is an input parameter or this is a measurable quantity. Similarly, alpha, this alpha it is just the average alpha. So, it is the area average alpha which you can very easily measure either by the conductivity probe technique or the radiation attenuation technique and so on and so forth. Okay. So, therefore, this is a much more friendly quantity or a much more determinable quantity as compared to this. So, therefore, these concepts have to be very clear. Now, remember one thing, certain concepts you have already learnt in single phase flows. For example, this area averaged value, this you have already learned in single phase flows, is not it? In single phase flows, very frequently you are supposed to find out the area average velocity, for which you are given a velocity profile, you integrate the velocity profile over the entire area divided by the area, you get the your cross sectional average velocity, or in other words, you integrate the entire profile, you get the volumetric flow rate of that particular fluid over that particular area. So, this area averaged value of this property, where the property is averaged over the entire cross sectional area, you are already familiar with, is not it? But the weighted mean value, this is also a pretty, I should say, a pretty straightforward. It is just the weighted mean value which gives you the void means the total distribution divided by the void fraction or divided by the area over which it is distributed. For P2, it is alpha P2 by alpha. If it would have been P1, it is 1 minus alpha P1 by alpha. So, therefore, this particular property, considering the effective area over which it is divided, The previous one was over the total area. This is the effective area over which it is distributed or divided. So, that particular effective area is considered, and from there we get the void fraction or the weighted mean average property of any particular parameter. Okay. So, accordingly considering these particular things or these particular concepts, what has been done, the different mixture properties they can be defined. For example, the rho T p it can be defined, the local in situ velocities can be defined. Similarly, you can define a u1 as well in this particular case. U1 would have been given as it is nothing but 1 minus alpha u1, or rather it is better written as u1 bar equals to 1 minus alpha u1 divided by 1 minus alpha. So, at each point you find it out and then you do it. Similarly, suppose you would like to define UTP, the two phase mixture velocity. It is nothing but rho Tp UTP divided by rho Tp. Okay. So, therefore, this is given as alpha, again rho 2 is taken as constant u 2 bar plus 1 minus alpha rho 1 u 1 bar divided by rho T p. This is the thing. And in the same way, if you find out the volumetric flux say J T p, this is J 1 plus J 2. Okay. This is nothing but alpha u 2 plus 1 minus alpha u 1. Okay. So, in this particular way we can continue and we can define all the different properties. Okay. Now, let us see how easily we can introduce some particular correction to the 3-dimensional drift flux model in order to arrive at the 1-dimensional flow situation. So, the basic definition which I had put it in this particular case is that this is the actual 3-dimensional or rather this is the actual drift flux model which we can define, is not it? From this particular model or from this particular concept, now a very rational approach to obtain the 1-dimensional drift flux model will be to integrate the 3-dimensional drift flux model over a cross sectional area, and then we can introduce proper mean values. Okay. We can integrate this by using this particular formula over the entire flow field and over the entire cross sectional area, and then we can introduce proper mean values. Now, remember one thing, whenever we have to deal with this particular equation, finding out J 2 is very easy. It is nothing but q 2 by A, as I have already written down here. This particular J 2, this is nothing but q 2 by A. J 2 1 it can be found out by it is just the average drift flux averaged over the entire area. So, this also can be found out easily. Now, for finding out alpha into J T p, what you have to do, for each particular point you have to measure alpha, at each particular point you have to measure J T p, you have to multiply the two and then you have to integrate the entire functional form. Now, this is not very easy. So, a simplified approach is that if we can replace this by some other easily measurable or input parameters. Now, how to do this? Now, for this particular thing, now certain things that I have told you, this needs to be replaced. Now, if I write down the equation once more, J 2 1 plus alpha J T p. Now, this term we know that definitely alpha J T p, this is not equal to this term, is not it? And this is a measurable parameter, where this alpha J T p is nothing but q 1 by plus q 2 by A, and alpha can also be measured. So, instead of this, if we can replace it by this term along with some other corrections, then probably my equation becomes a little more friendly. isn't it? So, if that can be done, then it becomes slightly little more easier. Now, how to do this? Now, if you remember in single phase flow, see wherever we get stuck, we resort to single phase flows. Okay, what has been done for single phase flows, accordingly we would like to do it here. Now, in single phase flows, if you remember that when we had considered your the momentum flux and say suppose when we considered the momentum, if you remember the momentum correction factor and the kinetic energy correction factors alpha beta, okay, in single phase flows. There what we did, just to keep the matter simple, what we did was momentum flux say in a pipe with velocity profile and uniform density. So, this is given as integral u square dA, where this is nothing but a rho u square, is not it? Now, we knew that this a rho u square, this is not equal to a rho, is not it? And but this is a much more easily measurable parameter. Okay. So, why? Because you just measure the velocity profile and then you integrate it, find out the profile and then you square it. But for this particular case, you have to measure the velocity at each and every point, you have to square it, then you have to find out the profile, then you have to integrate it. So, in single phase flows what we did, we just took the ratio of these two and expressed it as a correction factor. If you remember, this was the exact thing which we had done in Bernoulli's equation. If you remember Bernoulli's equation, the basic equation, it is just u square by 2 plus z delta p by rho plus delta u square by 2 plus, and then we introduced a correction factor alpha there, is not it? The alpha was the kinetic energy correction factor. Why did we introduce it? We introduced it just for this particular reason, just for, because if we introduce the correction factor, then we can take up the average velocity and we can square it and we can use it. But otherwise, it is actually the velocity profile for each particular point, the velocity has been to be measured, it has to be squared, accordingly the profile changes, that profile has to be determined, that has to be integrated and then we can use it. You remember this? So, therefore, in single phase flows what we had done for kinetic energy, even for momentum flux, when the density is constant and there is a velocity profile, what we did, how to express those things, we had introduced a suitable correction factor. What was the correction factor there? The for simplicity, a correction which was nothing but the ratio of this divided by this particular ratio, this was introduced as a correction term, keeping in mind that this particular correction factor will be equal to unity for truly one dimensional case and not far from unity for the general case. So, it has to be u square. Oh, sorry, very sorry. This is written in a very bad way. It is all right. So, therefore, usually what is the concept of single phase flows? In single phase flows we find that more or less the ratio of these, they are not very far from unity. Okay. And for truly one dimensional case they become unity, because for truly one dimensional case what is the case? The velocity is the same for all points in the cross section. Okay. So, therefore, this correction factor which is equal to 1 for truly one dimensional case and not far from unity for the general case. So, therefore, this was in this particular way the correction terms were introduced. Okay. Similarly, a similar approach was taken for this particular term here, this alpha JTP. Okay. Instead of alpha JTP, if we can replace it as alpha averaged, JTP averaged into a correction factor, then the situation becomes simpler, provided the correction factor equals unity for truly one dimensional case, it is not far removed from unity for the general case. Okay. So, therefore, keep it just by using this particular concept, it was thought that in the same way, suppose we can refer this as the ratio, this particular, this can also be introduced as a correction factor, and then using the correction factor we can write down the equation as J2 equals to J21 plus say alpha JTP into the correction factor. Okay, where this factor will be equal to unity for the general case, sorry, for the truly one dimensional case, not much removed from unity for the general case, and then we find that in this particular equation this can be obtained from Q2 by a measurable parameter. This is Q1 plus Q2 by A, again a measurable parameter. Alpha can be obtained from your simply void fraction measurements, and J21 from the drift flux correlations. We had already discussed the different drift flux correlations, they are all for truly one dimensional cases. Okay. So, therefore, this becomes much more easier. Now, this correction factor was first, it was proposed by your Zuber and Findlay. This is usually known as a distribution parameter. This is defined as C0, which can be defined as, the C0 can be defined as alpha JTP by this is the definition, or in other words if you break it down, this is 1 by A integral alpha j dA divided by 1 by A integral alpha dA into 1 by A integral j dA. See if this particular till this portion it is clear to you or not. Is it clear to you? Just to make corrections to the simple one dimensional theory, what we did? We first wrote down the actual equation in the form of averaged quantities. Okay. Now, all these quantities, they are area averaged quantities, where these area averaged quantities can be defined in this particular form. Okay. And next, after this what we did, once this could be defined, then we found that more or less this can be obtained from a easily measurable parameter. This is also the area averaged value. This creates a problem. Now, this is a product of two particular quantities which vary, which might vary across the cross section. So, therefore, what has to be done? The volumetric concentration has to be measured at each and every point, your overall volumetric flux has to be measured at each and every point, then the product has to be made and then it has to be integrated. For engineering applications, this is something very, very difficult. We would always like to keep matters simple while not sacrificing much on the accuracy of it. We would not like to go into something very, very complex, do a lot of mathematics, waste a lot of time and then get a very accurate results, where a little loss on accuracy would not have been much loss to us if the matters could have been made simple. And we are doing it in several engineering applications. In single phase flow also we have done it for the momentum correction factor, kinetic energy correction factor, etc., etc. We had introduced a correction factor, keeping in mind, see, whenever you introduce a correction factor, something has to be kept in mind, that for it reduces to some particular boundary conditions. For example, the correction factor equals to 1 for truly one dimensional case, and for other cases it is not very far. Suppose the correction factor becomes 5, 7, 10, 11, then it is not worth. If it is not very far removed from unity, then this particular concept, it works very well. That means the correction is not very much, isn't it? It is a very small correction. You can get the small correction by a large number of mathematics, or you can introduce some particular constant where that particular constant has to be evaluated accurately. So, these are the general concepts which we use even for single phase fluid flow. So, based on these concepts, what we decided was, since finding out this particular term becomes difficult, so if we can break it down into two terms and then introduce a correction factor which is nothing but the ratio of the two, then we can get this expression in a much more simpler, much more user friendly form. And this particular correction term, this is defined as a distribution parameter, this or a Zuber and Findlay parameter, since they were the first researchers to propose this particular concept for two phase flow, and accordingly this distribution parameter has been defined, and this makes the above equation, the form of the equation now becomes something of this sort. So, this becomes the form of the equation, now it becomes something of this sort. Okay. So, therefore, in this particular term we find that if we can find out C0 and if we can find out J21, then more or less this equation can be used for finding out alpha, or for all practical purposes this equation can be used. Once we can find out alpha from this equation, this alpha can be substituted in rho, Tp, U2, U1, kinetic energy terms, momentum flux terms, etc., etc., and all the terms can be deduced accordingly, and these terms when they are substituted in the pressure drop expression that we have obtained from the homogeneous flow model, we can get a much more accurate estimation of pressure drop as well. Correct? So, therefore, the next discussion goes on how to estimate this C0. Once we have certain ideas about estimating C0, it becomes much more easy. Now, before that I would like to write this particular expression is usually written in a slightly different form. What is the form? The original expression is something of this sort. Usually dividing throughout by alpha, what do we get? We get something of this sort, okay, where we know this particular term, what is this? This is nothing but alpha u2 by alpha, isn't it, which is nothing but u2 bar, the weighted mean velocity as I have already defined. Okay. And so, therefore, u2 bar equals to J21 by alpha plus C0. So, therefore, this can be defined, and we know that this is a much more convenient term as compared to u2 bar. This is a much more convenient term because this can directly be related to input parameters like the overall volumetric flow rate and the mean volumetric concentration, and so therefore, this is much more it is a much more input parameter as compared to this, and so therefore, we define this particular equation by considering the weighted mean average velocity. Okay. This is given as u2 is nothing but q2 by a, or in other words, in terms of measurable parameters, if we write, this is nothing but q2 by a alpha, this is equal to C0 q1 plus q2 by a plus J21 by alpha. Okay. In this particular way we can write it down, or in other words we can write it as u2 bar equals to J2 by alpha equals to u2j. This can again be written down as u2j, isn't it, because this is alpha into u2j. If you remember the basic definition of J21, what was the basic definition of J21? Alpha into u2 minus j, okay, it is nothing but alpha into u2j. Fine. So, therefore, we know this J21 by alpha, I will go to the next page. So, therefore, if we write down J21 by alpha, this is nothing but alpha u2j by alpha is nothing but u2j bar, isn't it. So, therefore, the previous equation which we were writing, this particular equation or this particular equation, we can also write it down as u2 bar is nothing but it is u2j bar plus C0j. So, in this particular way also we can write down the equation in terms of two weighted mean average values, the weighted mean average value of the velocity of phase 2 and the weighted mean average value of the drift velocity. So, from this particular expression, not from this, sorry, from this particular expression we can get the expression of alpha, this is equal to Q2 minus A J21 divided by C0 into Q1 plus Q2. So, therefore, if Q2 and Q1 they are measured, A is known, if J21 is known and C0 is known, alpha can be very well determined. Till this part, is it clear to all of you? Till this part. So, for finding out J21, what do you need? For finding out J21, you need two things. One is dependence of J21 on alpha, and the second thing is variation of alpha across cross section. If you know these two things, then in that case, because this J21, this is nothing but 1 by A J21 dA. So, therefore, you have to find out two things. One is how J21 depends upon alpha, okay, and how alpha varies across the cross section. If these two data are known, therefore, your J21 can be easily found out. Okay. And one more thing that we also know is, suppose say J21 is much smaller as compared to Q2. Okay. If J21 is much smaller, then what happens to this particular expression? If your J21 much less than Q2 or Q2 by A, sorry, then in that case your alpha becomes 1 by C0 Q2 by Q1 plus Q2, or in other words, if the drift velocity or drift flux is very small, that means the two phases are moving at almost equal velocity. Under that circumstances, we just need a distribution parameter in order to account for the non-uniform velocity and voidage profiles. And therefore, under that circumstances, simply the homogeneous value has to be modified by the term 1 by C0 in order to account for the non-uniform velocity and the voidage profiles, and accordingly this particular correction it is found out. Okay. But under normal circumstances, we find that generally we have this term J21, this is usually not very small, we have to account for it. Okay. And when we find that your J21 is also very small compared to Q2 by A, and the more or less the velocity and voidage profiles are flat across the cross section. Under that circumstance, what happens? A circumstance where J21 is much smaller as compared to Q2 by A. That means, both the phases are moving at a more or less uniform velocity, and your C0 is near to unity. That means, the velocity and the voidage profiles are more or less uniform. That means, more or less it is a flat velocity profile, and the dispersed phase is more or less uniformly dispersed in the channel or in the conduit geometry. Under that condition, C0 equals to 1, J21 is much less than Q2 by A. For these two conditions, what happens? The expression of alpha reduces to, you can observe the expression of alpha, where this is very small, this term goes away, and this is 1, this term. So, therefore, it becomes the homogeneous flow value, is not it? So, therefore, you please understand what does the drift flux model do. It accounts for the relative motion of the two phases, it accounts for the non-uniform velocity and the voidage profile. So, this is the thing which I would like you to know, that for if concentration profile is uniform across channel cross section, C0 equals to 1. If U to J is much less than Q2 by A, then for these two cases we get flow becomes essentially homogeneous. Okay. And then what happens in this particular case, the relation between your when this happens, under that particular circumstance, what happens? If we go a little further, we find that this has become equal to unity, this term has gone off, then the relation between this and this, it gives you a straight line passing through the origin at an angle of 45 degrees to the x axis or the y axis. Okay. So, therefore, under that circumstance, what happens? The relation between, in this case, relation between mean velocity and flux reduces to a straight line through the origin at an angle of 45 degrees. Or in other words, for such a circumstance, if we plot if we plot your u2 bar with j, we get a straight line through the origin, isn't it? We get such a straight line. Okay. And the thing is, what we usually do, and this gives you the homogeneous flow theory. Okay. Now, for this particular case, what we get is that usually what we do, whenever we get an experimental data, we try to plot it on this particular curve with the 45 degrees line on it. Okay. And then we see the spread of the data. From the spread of the data, we try to understand how much it has deviated from the homogeneous flow theory. Accordingly, we introduce corrections. Do you understand? Usually, whenever we have any particular experimental data, what we do, we usually when it is for fully developed velocity and void profile, okay, for fully developed velocity and void profile, what we try to do is we make such a plot, and then in that particular plot we substitute the data around this 45 degrees line. Okay. And then we find out that usually data point will be clustering around this particular line. The amount of spread it has from this line, that particular spread tells us how much it has deviated from the drift flux theory, and whether we should go how much it has deviated from the homogeneous flow theory, and whether we should go for some correction or not, and in what way should we introduce the correction, whether C0 is important or whether J21 is important. Usually we find that J21 is important and some particular J21 has to be incorporated there. Correct? Now, the next thing which I would like to discuss is the estimation of C0. Okay? How we can estimate C0s, or how C0 can be obtained for different particular flow situations. Now, if you see here, I have already written down some in this PPT. If you observe, then we find that in the PPT I have written down the basic equations. Okay. This PPT, if you observe this PPT, then you find that in the particular PPT I have just written down the basic equations. You can always go through them and you can find out that more or less the basic things are written here. So, C0 is the ratio of the average of product of flux and concentration to the product of the averages. This is the basic definition of C0, and then using this particular definition we come across this particular friendly equation based on input parameters, from where alpha can be obtained by using this expression. Here we find if J21 and C0 is close to unity for fully maybe when the velocity and the concentration profiles are flat, and when J21 is much less compared to Q2 by A, then alpha reduces to the homogeneous flow value. Now, the usual trend to find how much the actual situation deviates from the homogeneous flow value, we usually plot this particular term with this particular term, and then the deviation of the data from the 45 degrees line passing through the origin gives us an idea about the magnitude of C0 and J21 by alpha. Okay. So, next is estimation of C0. Now, what are the different ways by which you can estimate C0? Now, there are two ways. The first thing is you construct such a type of plot. Now, if you construct such a type of plot, then in that particular plot usually what we find is that it usually, since I have told you C 0 is not much removed from unity, is not it. So, we find that if we make such a plot, or in other words if we make a plot of say q 2 by q 1 plus q 2 by a, then usually we get a straight line. Okay. The best fit curve is usually a straight line. And can you tell me the slope of this straight line what it gives you and the intercept of this straight line what it gives you? You can see the basic equation and you can tell me what we get from the slope and the intercept of this particular straight line. Slope gives you C 0 and this gives you J 2 1 by alpha, is not it? So, therefore, very simply usually we find that for fully developed velocity and voidage profiles, please remember this, for fully developed velocity and voidage profiles usually we find that when we do such a plot, it gives the best fit curve is a straight line. Okay? When the local drift velocity is constant or it is negligibly small. In that particular case, your slope, it gives you the slope of this best fit line, this gives you the value of the distribution parameter C 0 and the intercept gives you the value of the weighted mean local drift velocity. Okay, this gives you the weight, or in other words this gives you u 2 j, okay, which is nothing but the weighted mean local drift velocity. So, this is one particular way by which we can find it out, and we have done it several times. What we do whenever we have to analyze experimental data, first we refer to such a plot, we find how much is the deviation. When we find the deviation is quite large, then we resort to this particular plot from where we can find out C 0, we can find out u 2 j bar, and once we find these out, we can find out all the other qualities, all the other parameters. And but this is usually done for fully developed velocity and voidage profiles. When it is varying with time, definitely for temporal variations we cannot resort to this. Okay? But apart from this, we find that there are certain other ways also by which we can find out C 0. What are the other ways? If we go to the basic definition of C 0. What was the basic definition? So, the ways of finding out C 0, one is from this particular equation, which is q 2 gives you so this particular equation, when we plot this versus this, then we can get C 0. The other thing is, what is the basic definition? Basic definition is alpha j by alpha j, okay? Or in other words, if we go to the actual definition, this is this is the other definition. So, what we can do from the velocity profile and the concentration profile also, we can find out C 0. This can be the other way, is not it? Usually what we assume parabolic or the power law profiles. Okay? Usually the type of profiles which we assume are power law profiles, which give you j by j 0 equals to 1 minus r by r whole to the power m, alpha minus alpha 0 by alpha 0 minus alpha w equal 1 minus r by r whole to the power n. Okay. Usually we have such power law profiles. Even in single phase flow also you have found out that usually we deal with the power law type of profiles. So, when we have such type of profiles, where you remember that alpha is the average volumetric concentration at any particular radial location r, alpha O is at the center and alpha W it is at the wall, which is usually equal to 0. Same thing, j 0 is at the center and this is the radius and this is the radial distance. So, for such a situation we find that C 0 it can be given as 1 plus 2 by m plus n plus 2 into 1 minus your alpha 1 minus alpha by alpha. Okay. So, this I have already written down in the PPT. Okay. If you observe the PPT, then you find that this particular C0, it has been derived for power law profiles of alpha and j. Several researchers have worked on different aspects of your drift flux model and how to find out C0, and it has been found several researchers have proposed different particular values of C0. Some people have said that C0, it is a function of density ratio as well as the Reynolds number. Okay. And accordingly, several different definitions of C0 have been proposed, which you can use for as the case may be. They are empirical correlations which have been derived from a large number of data. For example, for fully developed flow in a round tube, please remember C0 has been expressed as a function of rho g by rho l. Again, for fully developed flow in a rectangular channel, it has been developed in this particular way. When it is not fully developed, then in that case the expressions are given here, and accordingly I have written down a large number of expressions from where your C0 can be obtained under different conditions. But please remember, these were all for more or less parabolic type of voidage profiles, where we assume that the voidage is much more higher at the center as compared to the walls. Okay. But if the situations change, say by some example, maybe say there is a heat flux and there is intense vaporization at the walls. So, under that condition, the profile, instead of becoming this, it becomes this particular shape, from concave it becomes convex. So, in such particular cases, we find that the C0 calculation has to be done from the basic equation that I have written down here. Okay, from this particular basic equation, it has to be done. For two particular cases, one is when there is a heat flux and there is intense vaporization at the walls. So, therefore, there is a larger vapor concentration at the walls as compared to the center. The other is when we are introducing air through, say, a porous wall. Then in that case, what happens in the developing region, there is greater concentration of air bubbles at the wall as compared to the center. For such particular cases, we cannot use the C0 values which I have written down in my PPT. They are mostly for fully developed flow cases or for those particular cases which have a convex sort of a profile. So, for anything else, C0 has to be derived from the basic equation which I have written down. Okay. And one more thing also which I would like you to remember in this particular cases, usually by whatever way you find out C0, usually C0 it varies from 1 to 1.2. As I have told you, it does not deviate much from unity, it varies, it lies close to unity, and usually for normal circumstances it has a maximum value of say 1 to 1.2 or 1 to 1.1, it does not vary more than that. And finally, the last word of caution which I would like to give you regarding the drift flux model is, see, in this particular model we consider the volumetric flux, the velocity, everything as vectors. If that is the case, then the direction becomes very important. For example, for all the cases co-current upflow, co-current downflow, I have been considering the upward direction as positive. Okay. That is why J2 was positive, for counter current flow J1 was negative, when liquid was flowing down, etc. So, remember one thing, sign convention is very important as far as the drift flux model is concerned. There are several sign conventions which we take. The first one is usually the direction of flow is taken as positive, or the upward direction is taken as positive. Now, we find that most of the two phase flow analysis, what we do, we give more importance to the dispersed phase. That is why we have defined alpha as the volumetric concentration of the dispersed phase, is not it? We do not define 1 minus alpha, we talk in terms of alpha. We usually talk in terms of J21 rather than J12, is not it? So, usually we find that the direction of motion of the dispersed phase or the discontinuous phase is taken as positive. There can be situations where the direction of gravitational force is taken as positive. You can do whatever the case may be, but remember one thing, whatever direction you are taking as positive, you have to define that in the beginning of the problem, considering this direction as positive, the following momentum analysis follows. So, this has to be referred to before you do any problem. Sign convention is very important for the drift flux model. So, this completes our drift flux model, and from the next class we are going to start the two fluid model or the separated flow model. Thank you very much.